6.1 is on page 4 or 5, talks about the basics of counting techniques. So we need to figure how many possible ways could we do an event. We start with what's known as the product rule, and this is like the most direct and simplest way of counting how many ways can we finish a task. Suppose that a procedure can be broken down into a sequence of 2 tasks. We start with 2 and then we build on it. If there's n ways to do the first task, and for each of these ways doing the first task, and 2 ways to do the second task, and there are n1 times n2 ways to produce such tasks. Now, this is how I always remember it from combinatorial statistics. If I have a choice, I add. If I don't have a choice, I multiply. So if I must do those 2 tasks, you multiply. And later on, if you have a choice, you add them. So on page 416, I'm going to start with the first problem. An office building contains 27 floors and has 37 offices on each floor. How many offices are in the building? Well, here we have, there are 27 floors and you don't have a choice. Each floor has 37 offices. So how many offices are on the entire floors or the whole building? That's the product of those, whatever that number is. A particular brand of shirts comes with 12 colors. It has male or female version. Comes in 3 sizes for each sex. How many different types of shirts are there? Well, let's see. There are 12 colors, and you must choose male or female. That's 2 of them. And you must choose a size. You don't have an option of that. So whatever that number is, that's how many different types of shirts are made. So if you make that many shirts, you'll have 1 of each. There are 4 major routes from B to D and 6 from D to LA. How many major routes are there from B to LA? Well, to show you another way of doing this, there are 4 from B. So if I start at B, the alternative is a lot of work. I could take 1 of 4 routes to D. I could take route 1, route 2, route 3, there's 4 of them. And once I get to D, I could take 1 of 6. This is the tree method. So if you count how many total outcomes are there, there are 24 total outcomes. Now imagine, or routes I should say in this case. So imagine now, if there's 40 and 60, listing is not an option. We're trying to figure out the total. We're going to come back to this in the future sections and use that for many applications. How many different 3-letter initials? So you have 3-letter initials, 1, 2, 3. With none of the letters repeating, can people have? So if I want to do initials, well, there are 26 letters. If you can't repeat, once I choose 1, now I must choose the other. There are 25 of those. And for the third, since I chose those 2, now there are 24 left. And that would be how many different initials now? How many bit strings are there of length 8? Well, 1, 2, 3, 4, 5, 6, 7, 8. For the first, I have 2 choices. Another 2, another 2, all the way. So that's really 2 to the 8, which is like 256 bits. Now, if a task can be done either in 1 of n sub 1 ways or 1 of n sub 2 ways, where none of the sets n1 ways is the same as n2, so they're distinct, then there are n sub 1 plus n sub 2 ways to do the task. bit strings are there of length 6 or less? 6 or less. So it could be 6 or 5 or 4 or 3 or 2 or 1 or 0, but they say not counting the empty set. If you don't count the empty set, well, we're talking about bit size. Here, just like the previous problem, there's 2 to the 6, or since I have a choice, I add 2 to the 5th, or 2 to the 4th, or 2 to the 3rd, or 2 to the 2nd, or 2 to the 1st, whatever that is. Now, if they would have said less than or equal all the way counting to 0, then I could say that would be saying at least. So this is at least 1. Well, think about it. That's really what this is. At least 1. We could have none. We could have 1. We could have 2, 3, 4, 5, 6. These are all the possible outcomes, right? 6, all the way to 1, 0, 1, 2, 3, 4, 5, 6. So, if this is all the possibilities, and I say I want at least 1, then I'm talking about, then that is the total minus the 0 specifically. The total choices 1, 2, 3, 4, 5, 6, 7 choices. There's 2 to the 7th minus the 0 is really, there's only one way of doing that. That's the empty set. So that would be 2 to the 7th minus 1, which should be exactly that. So anytime I'm doing at least 1, I can take the total minus none. At least 2, that will be the total minus the first 0 or 1. And that idea is going to help me in the long run as I move on through the problem. But this listing is fine for now. I'm not really enforcing that rule yet. We're going to get there in later sections. They say, how many bit string of length n, where n is a positive integer, start and end with a 1? Well, let's say 2. Start and end with a 1, that's really 1 of 1. If you have 3, you have 2 choices inside, either a 0 or a 1, so that's really 2 of them. If you have 4, starting with a 1 and ending with a 1, you have a 0 or 1 or 0 or 1, so you really have 4 altogether. And eight, so that's really like 2 to the 0, 2 to the 1, 2 squared, 2 cubed. So if I have 2, it's 2 to the 0. If I have 3, 2 to the 1. If I have 4, 2 squared. If I have 5, 2 to the 3rd. So if I have n, it's really 2 to the n minus 2. That's really how this works. That's the part I was mentioning. If a task can be done in either n sub 1 ways or n sub 2 ways, then the number of ways will be n sub 1 plus n sub 2 minus the overlap, the common to both. And this could apply in many examples. The first example I want to attempt, this is a hard problem to do if you're going to do it forward. It says, how many strings are there of 4 lowercase letters that have the letter X in them? The issue is X could be, if it has X, that means at least 1X. At least 1X is a lot of work. That means either here, or 2, or 3, or 4. It doesn't mean X is here, that's going to go in the first. So just to show you, the X could be there, or there, or there, or there. Or, that's 1X. You could have 2 X's. So as you see, this is going to be a lot of work. Or so at least is not that simple. Or 3 or 4. Well, instead of doing that, we could say if at least one x, that is the total minus no x's. And the reason that's easy, the total will be, well, what are the total possible choices? 26 letters each. So that's 26 to the 4th minus, how many ways can you have no x's? Well, omit the x, omit the x, omit the x, and omit the x. And that's how many ways you can do that. Taking the total minus none is really the way to go. In probability, we say that's 1 minus the complement, but 1 is really the total number, 100%. Here we're dealing with the counting techniques, yet we're not into probability. It's easier to explain that in terms of probability than it is in terms of counting. The DNA sequence is A, C, G, and T. There's 4 of them. So it says how many 5-element DNA, 1, 2, 3, 4, 5, end with an A. Well, to end with an A, you can only choose one there. And here, you could have 4, 4, 4, or 4. Since you don't have a choice, you multiply those. That would be your answer. If we go by B, start with a T. 1, 2, 3, 4, 5. If you start with a T, then there's only one way of doing that. And ends with a G, there's only one way of doing that by putting a G there. But here you could have 4 each. So you could have 64 possible choices. Contains only A's and T's. Only A's and T's. How many choices? Well, A or a T, A or a T, A or a T, A or a T, A or a T. Do not contain a C. Well, we're going to take 1 out. That's 3 each. So that can be 3 to the 5th. When we do probability, this will make a lot more sense. And we're going to switch to a slightly different, but same idea. Oh, that's 27. I meant 26. Let me see. Let me get 26. Give me a second. Okay, we're back. How many strings of 4 decimal digits? Do not contain the same digit twice. So if you don't want them, for the first you have 10 choices. Since you can't repeat, you're going to have to choose the second to be, there are 9 choices once you choose the first. Now that you choose the first 2, there's 8 and a 7, whatever that is. End with an even digit. If it ends with an even digit, it could end with a 0, 2, 4, 6, 0, 2, 4, 6, or 8, 5 of them. And here, now it didn't say they do not repeat. Since they didn't say that, well, they could have 10 choices each, 0 to 10. Actually, take that back. End with an even digit, end with an even 0 to 1. There's 4 of them. Oh yeah, that's it. Okay. And how about have exactly 3 digits, have exactly 3 digits of 9. Exactly 3 digits of 9. So that's 1, 1, 1. And here you could have 9. Okay, I should put it this way. I want this to be 9, 9, 9. And here it could be. So I don't mean 9 choices. I mean the number 9 right there. There's only one way of choosing that, one way of choosing that, one way of choosing that. And here you have really any number 0, 1, 2, 3, 4, 5, 6, 7, 8, but you can't have a 9 because you want exactly 3 9s. So here you have 9 choices, but you could have had a 9 there, a 9 there, and a 9 there. And this could have had the 9 choices. So let me color code those. That could have been right there. Or so there are 9 ways I can get this, 9 ways I can get this, 9 ways I can get this, or 9 ways I can get this. Since I have a choice, this or this, I add those. That is 9 plus 9 plus 9 plus 9. So that's 4 times 9, 36. There are 36 ways I can do this. So if you have a choice, you add. If you don't have a choice, but here's the hard part. You really need to take into account all possible ways you can have 3, right? So you could have 9, 9, 9, and you could put any number other than 9 there. Or you could have 9, 9, a number and 9. Or you could have 9, a number, 9, and 9. Or you could have a number 9, 9, 9. Okay. Now 28, it says, how many license plates can be made using either 3 digits followed by 3 uppercase letters, or is a choice, 3 uppercase followed by 3 digits. Well, okay. How many digits are there? There's 10, 10, and 10. And how many letters are there? 26. Assuming you could choose them, let it say you can repeat. Or you could have the letters first, then the digits after. So 2 times whatever this number is. That's a massive number, of course. How many license plates can be made using either 3 uppercase, let's see, 3 uppercase English letters followed by 3 digits. So uppercase 26, 26, 26, 10, 10, 10. Or 4 uppercase 1, 2, 3, 4 followed by 2 digits. Okay, whatever that is. Alright. 32. How many strings of 8? So we have 8 in each case. So 1, 2, 3, 4, 5, 6, 7. English letters are used there if letters can be repeated. That's 26 each. That's 26 to the 8th power. Massive number. How about if no letter can repeat? Isn't that 26 for this first? 25, 24, 23, 22, 21, 6, 7, and 8. Whatever that number is. That starts with an X. So the first letter is an X. There's only one choice of doing that. If the letters can be repeated. And isn't that going to be, so that's going to be 1 times 26 to the 7th, because there's 7 of them. That starts with an X and no letters can repeat. So that's 1 times 26. Not 26, you already chose an X. 25. Start with an X, no letters can repeat in this case. So here you can have all X's. 25, 24, 23, 22, 21, 20, and 19. So again, the first is an X. Since it can't repeat the second choice, you have 25 choices because X was already chosen. If we go for E, that starts and ends with an X. The first and the ending is an X, so that's 1 choice each. If the letters can be repeated, so that's 26 each, that's what? I think that's 26 to the 6th power, right? F, that starts with the letters B, O in that order, so 1 and 1. If the letters can be repeated, well, there's the remaining 6, that's 26 to the 6th power. Starts with the letter B, O. Oh, and ends with the letter B, O, 1, 1, so that's 4. There are 4 slots, 26 each. That's 26 to the 4th power. That's how many different letters you could have. That starts and ends with BO. Again, one in one way, because you must choose a B, you must choose an O. But what's in between now, in that one, if the letters can be repeated, we just did that. That starts and ends with the letter BO. If the letters can be repeated. That starts, or ends. That starts or ends. Okay. Take that back. So starts or, it's a choice, ends with the letter BO. 6, 7, 8. So this is 26 to the 5th. This is 26 to the 5th. You add those. That's the resulting part for number 30. Now, I did want to point out a tree diagram. We're going to need to figure this one out later on. For now, I just want to introduce it really quick. This is from the book. I pretty much stole it from the book. Normally, I like them to go to the side. They like it coming down. Doesn't really matter. So if I choose my bits, it's wise to choose. I choose up 1, down 0, and that's how we really figure out second choice. So if I really read just the far ends, 1, 1, 1, 0, 0, 1, 0, 0. I'm not going to go into detail about that because we're going to use that later on heavily when we do graph theory. So I'm saving it until we get